It'll disappear on its own.
There we go.
Good afternoon, and welcome to session 2 of the CERC Doctoral Students Forum. Our first presenter of this session is Abheek Chatterjee, who is a mechanical engineering doctoral candidate advised by Dr. Astrid Layton at Texas A&M University. His research interests include system of systems architecture design, resilience, sustainability, and network analysis. Abheek, along with Drs. Malik and Layton, won the 2020 SEIKM Best Paper Award for his work on Ecology-Inspired Resilient System of Systems Design. He also received 4 departmental fellowships and a graduate summer research grant. Today, Abheek will present his work, Ecology-Inspired Design of Resilient and Affordable System of Systems. With that, I will turn it over to you.
Thank you, ma'am. Can everybody hear me?
Yes, all good.
Thank you. Thank you for the introduction, and thank you for this opportunity to present my work on ecology-inspired design of resilient and affordable system of systems. System of systems are a networked integration of constraint systems that in themselves fulfill specific roles, are independently operated, and are managed and are often geographically dispersed. And they're integrated to help achieve new capabilities that would not be possible by using these constraint systems by themselves. Examples of system of systems include military and aerospace operation networks and critical infrastructure networks such as power grids. And stakeholders in system of systems are interested in multiple attributes such as performance, resilience, and affordability. The focus of this research is on resilience, that is defined as the ability of the system of systems to survive and recover desirable performance in the face of a disruption. Now, while resilience is a highly desirable attribute, designing for resilience is very challenging because resilience cannot be precisely quantified without detailed disruption models that are usually not available in the early design stages. Also, the scale and complexity of system often means that there's a large number of possible disruptions, and it is not feasible to test every candidate architecture for all possible disruption scenarios. Therefore, the early stage design is usually guided by heuristics such as adding redundancy or using localized capacity. And while these are very useful guidelines, they're qualitative and therefore do not account for trade-offs with other efficiency-related objectives such as affordability. So the desired practice here is that if we could have some sort of proxy resilient indicators that could be used in the early design stages to filter poor system of system architectures and help us guide towards better ones, and we'd want that these indicators should have consideration for affordability and resilience trade-offs. And in my research, I look at ecological architecting principles as a potential solution to the problem. So if we look at ecosystems in nature, they can be seen as biological system of systems, where the individual species are like independent constituent systems that are acting in their own self-interest. However, the overall dynamics and the behavior of the ecosystem emerges from the complex interdependencies between these species, much like we see in engineering system of systems. And the biological ecosystems are resilient to random, small and large-scale disturbances that are common in their life. And the ecosystem manages to survive and grow as a whole. And those are desirable attributes that we want to design into our engineering system of systems. So in this research, we use a framework called ecological network analysis that was developed by ecologists to quantitatively study the architectural characteristics of biological ecosystems. And what we want is to take quantifiable design inspiration from these biological ecosystems and then apply them to the design of engineering system of systems. More specifically, this research investigates the value of ecological architecting principles as early stage decision support guidelines for the design of system architectures with desirable resiliency and affordability trade-offs. So if we imagine a large system of system design space which has all our candidate alternative architectures for a certain system of systems operation, then we can use ecological network analysis in the early design stages to filter out and limit our design space to the ecology-inspired architectures from which we can then use high-fidelity evaluation approaches that are there in the literature to get to our final resilient and affordable designs. And the potential benefits here are that because of the ecological inspiration, it can lead to novel designs, but maybe more importantly, it can help us reduce the design time and lower the computational and experimental cost of coming to the final designs. And I should stress here that the goal is not to replace the existing high fidelity evaluation approaches. Rather, it is provide a complementary toolkit that can be used in the early design stages when we do not have enough details and knowledge to use these high fidelity evaluation techniques. So I'll start with a brief introduction of ecological network analysis before I move on to the specific parts of the studies that I did. So ecological network analysis is a framework that ecologists use to model ecosystems as flow networks and then study their structural and functional characteristics. So to do this, ecologists look at the species within the ecosystem and then trace the caloric interactions between the species. So essentially the predator-prey relationships between themselves. They also trace the caloric relationships within the species and from the external environment. This leads to a directed network, and this directed network can then be mathematically represented using a flow matrix. And from this flow matrix, ecological network analysis allows us to calculate multiple metrics to evaluate the structure and functional characteristics. But one metric of special importance here is called the degree of system order, that quantifies the relative pathway efficiency or constraints in a flow network and is mathematically defined as the ratio of the measure of pathway constraints and the upper limit on pathway constraints. It is perhaps more intuitive to look at degree of system order over its spectrum. So degree of system order takes values between 0 all the way to 1. And a degree of system order value of 0 would represent a network architecture, as shown on the notional network on the left, where any flow going through any of these nodes would have multiple options for inputs and outputs. And that is called a highly pathway redundant or flexible network architecture. On the other end of the spectrum, we have networks with degree of system order values close to 1, where flow going through any one of the nodes in the network would be constrained to flow in one specific direction only. And so that would be called a highly pathway efficient or constrained network architecture. Before going forward, it should be stressed that the pathway redundancy terminology that is used here for network organization is based on the flow pathways and is not exactly the same as the redundancy in components or functionality as we see traditionally in engineering. However, there is a relationship between them, as will be clear through the studies that I'll present soon. So why are we interested in this metric of degree of system order? Well, it's because when ecologists studied these long-surviving biological networks using the metric of degree of system order, they found that these architectures avoided both excessive pathway redundancy and efficiency, instead opting to lie within a narrow range of degree of system order values called the window of vitality, because this unique balance allowed them effective resource utilization in the undisrupted state and also the ability to survive and recover from disruptions by remaining adaptable. And the research question that then came up was this: is this concept of window of vitality also applicable to engineering system of systems? And to answer this question, I designed a study to investigate the relevance of ecological network analysis in system of systems engineering, starting with a hypothesis to be tested that are ecologically similar system of system architectures, do they exhibit desirable resilience and affordability trade-offs? And to test this hypothesis, I followed the following strategy. For a hypothetical operation scenario, I generated a large number of representative system architectures. I evaluated the development cost, their performance under normal undisrupted situations, and their degree of system order values. Then, under different combinations of constituent systems or interaction failures, I assessed their resilience over a operation period using a metric from the civil infrastructure literature called the resilience loss. Now, at this point, I'd like to stress that the degree of system order evaluation could be done and was done before doing any of the disruption simulations for resilience assessment. And the significance of this will be clear very soon. So from the data that was collected here, I was able to perform two analyses. First, the analysis of the degree of system order values of the Pareto optimal architectures, and then also a resilience cost comparison of the system of system architectures that were within the ecologically identified window of vitality and those that were outside it. So I'll start with the resilience versus affordability trade space exploration. So here we have the resilience versus affordability trade space in the n-1 disruption scenario, which is the scenario where we have loss of one constituent system in the system of systems. And so on the y-axis, we have our resilience metric, expected resilience loss, and a lower value indicates a more resilient network to that specific disruption. And on the x-axis, we have development cost, and a lower value indicates a more affordable network. And if we look at the Pareto optimal architectures in this trade space, which are highlighted, we see that the majority of Pareto optimal system architectures lie within the ecologically identified window of vitality, as seen using these green diamonds. And the few non-window of vitality architectures that lie on the Pareto front here, they tend to lie on the extreme ends, which would not be very favorable in case we were looking for some sort of a balance or trade-off between these two architectures. While I'm showing the results here for the n-1 disruption scenario, these results, that is, that the majority of Pareto optimal architectures fall within the ecological window of vitality, was found to hold for all the 8 disruption scenarios that we tested, ranging from link loss scenarios all the way to multiple constituent system failures. Then coming to the resilience cost comparison. So I compared the architectures within the ecological window of vitality to those outside the window of vitality using a weighted sum of the two objectives, that is expected resilience loss and the development cost. And since both of these objectives needed to be minimized, a lower value of this weighted sum points to a more desirable architecture and a greater value points to a non-desirable architecture. And so for the n-1 scenario, under the weighting factor applied more heavily on minimizing resilience loss, we see that the window of vitality architectures significantly perform better than the architectures outside the window of vitality. And it is actually true for all the 8 disruption scenarios. Now, while here I applied a greater weight on minimizing the resilience loss, I also conducted the analysis with equal weight on both objectives and with greater weight on minimizing the development cost. And as you can see here, every time that minimizing resilience loss or maximizing resilience is of greater or equal importance compared to affordability, the architectures within the ecological window of vitality were found to fare better on this weighted resilience cost model. So the key takeaways here are that first, this study confirmed a relationship between the degree of system order metric and resilience and affordable system of system architectures. And if we recall, degree of system order could be calculated without needing detailed disruption simulations. And that adds up to the significance here that we can actually then use it in the proposed way that I was presenting earlier, that ecological network analysis can enable fast evaluation of large number of feasible system of system architectures in the early design stages for system of systems architecting, when we do not have the capability or the knowledge required to do more high fidelity evaluations. However, we have a few challenges in practically applying this approach. Well, what I mean here is that, well, the network models of the biological ecosystems that the ecologists were primarily concerned with, they were mostly concerned with the caloric transfers between the species, that is one single interaction type. And the input and output flows at all of these nodes were related using simple conservation laws. Whereas if we then come out to our network models of engineering system of systems, we need that we are able to take into account various distinct but interdependent interactions. And also inputs and output at the node can have more complex relationships and may not always be conserved. For example, if we look at information flows, new information can be generated or copied at constraint systems, and that does not violate any physical laws. So how do we account for such conditions? Well, for this, I proposed a modeling approach using a directed multigraph. And that is a graph that is permitted to have multiple directed edges between the nodes. So the nodes still model the constituent systems as earlier, but the multiple edges here allow us the ability to model distinct types of interactions. And so then the question becomes, how do we identify what are distinct types of interactions in this model? So for this, we turn to previous work in the hierarchical description of system of systems that is available in the literature. And there we see that while there's an overarching performance objective for a system of systems defined, to achieve that performance objective, we first have to meet some sort of requirement capabilities. And then for each of these requirement capabilities, we have system functional or task capabilities that need to be met. And based on this description, we can then assign distinct interactions based on the requirement capabilities of the defined system of systems. And then the interaction magnitudes can be assigned based on the task or functional loads at each of the constraint systems. And so the main features of this approach are it does not necessitate that all interactions used in this model have to be conserved. It does allow for transformation of interactions from one type to another and account for them in this model. And that this evaluation is scale invariant. So regardless of whether we change units or use different units for one of these interactions and not for the others, the evaluation of the architecture under this approach will not change. So I'm showing an example model using a notional cyber-physical system of systems. So where we have 3 main requirement capabilities, that is to operate and distribute the physical flows, but also these physical operations then need to be monitored, and finally they need to be regulated. And so this gives us the three different types of distinct interactions that we then model in this framework. And then using the task load setting of the system for the different interactions and requirement capabilities, we can have the interaction magnitudes. And then this directed multigraph can be represented using a 3D matrix, where for any element, the first two indexes I and j represent the source and sink node of the interaction, and the third index represent the type of interaction that it belongs to. And then we can use the modified ecological network analysis metrics that I came up with to evaluate the degree of system order of this overall system of systems. Now, while I'm showing the example using a notional cyber-physical system of system, I want to say that this proposed model is applicable to both networks with cyber and physical interactions, as well as with multiple physical flows or multiple cyber flows. In fact, that brings us to our first application here on a multi-commodity supply network. So from the literature, I was able to find a case study of an electric motor supply network with multiple component flows. Here, using the information from the case study, I was able to design a bio-inspired network architecture that was designed for ecological similarity. And I also designed a baseline network architecture for minimum shipping cost. I used two methods for evaluation of this network. So first was the export performance, that is the number of units being sold or exported out of the distributors here. And the second, number of active plants. So at any given point in time, how many of these plants managed to be operationally active. And I tested and compared the resilience of these two network architecture to a specific expected disruption scenario that was also presented in the same paper. And the results are here. So on these graphs, over the time period that is 12 weeks of operation, I present the export performance using the number of units sold and the number of active plants. And as you can see here, after the disruption at the end of week 1, the bio-inspired network architecture performed much better in both of these figure of merits compared to the baseline or design for minimum shipping cost. In fact, if we also compare the loss of profit that this hypothetical supply network would sustain, we see that the bio-inspired network does much better. So ecological inspiration for this network design has the ability to reduce cascading shutdowns, improve survivability, improve recovery, and reduce profit loss. But before going further, I would like to point out the limitations of the study, that yes, this was conducted with a specific set of operating conditions. So I mean specific selling cost and operating costs and a specific disruption scenario, but we are actually extending this, and in collaboration with another student in our research group, we are working on developing a multi-parameter study so that we can identify at different types of operating conditions if there are different degree of system order ranges that are more feasible for this bio-inspired design approach. The second application that I would like to present today is the cyber-physical power networks. So I was able to find a synthetic 8-substation cyber-physical power network from the literature. And so we have 8 substations at which we have the physical systems, so generators, loads, buses, and we have branches connecting and allowing for energy transfer between these substations. And there are remote terminal units at each of the substations for monitoring and regulation purposes, and there is a central SCADA terminal as well. So right now, I've done a preliminary design space exploration using ecological network analysis on this case study. Assuming that the physical infrastructure was fixed, I made alternative architectures by changing the cyber infrastructure design decisions. So the two decisions that I looked at specifically are communication network topology. So one, we can have a star topology where remote terminal units only communicate to the central terminal, and the mesh topology where the RTUs can communicate within each other as well as the central terminal. But I also did a design decision changes where it was the control authority could be distributed such that one, the control authority lay primarily or completely with the central terminal, or we could have that the decision authority lies completely with the local RTUs for the local physical systems, or it could be shared in some manner. And so by modeling them using the proposed framework and calculating the degree of system order values of these architecture alternatives, I was able to see some key observations from this preliminary study. The first, degree of system order was able to capture both topological and functional decentralization in architecture in this analysis. Second, we saw that topological decentralization going from star to mesh communication topology allowed for a greater pathway redundancy or flexibility, which was expected, but it's good that it was validated in our results as well. And finally, we found that the effect of decentralization of authority, so going from a central to shared to a completely local authority, was the effect of it on the pathway flexibility of the network was context dependent. So in some cases, it did make the system more pathway redundant. For example, in the star topology, going from central to a shared authority, but then going to completely local authority can actually make the system more pathway efficient or constrained. And that is because when we have completely local regulation, the cyber side of the network gets fragmented into small parts. And so the interactions then are limited to flow within those specific set of nodes, actually constraining the flow of information. So, as a summary of contributions here, I presented evidence supporting the relevance of ecological network analysis in resilient and affordable system of systems design. I presented guidelines and modified metrics for ecological network analysis of practical system of systems. Presented an application to resilient and affordable multi-commodity supply network design, and finally set up a design platform using ecological network analysis for cyber-physical power networks. In the future, I'm primarily looking at three areas. First, refining the system of systems ecological network analysis framework. So while we do have the guidelines set up right now, I want to formulate it in terms of a concrete algorithm. So for example, if we have a system of systems architecture defined in an already existing language such as SysML, we can take that as an input and then have the algorithm generate the ENA model for us. The second most important one, I think, is I'm working on identifying operation-specific favorable degree of system order ranges for system of systems. So, for example, if we go back to the supply network study, at different types of operating conditions, if we can identify small degree of system order ranges, so smaller than the ecologically identified window of vitality, then we can use those specific ranges, give them to practitioners as the heuristics to restrict the large design space into a very narrow space on which application of high fidelity evaluation techniques could be much faster and much easier. And finally, I'm working on identifying more windows of vitalities for system of system design. So what I mean here is now that we have seen promising results using the degree of system order metric, I'm trying to see if there are other metrics like degree of system order that can be used in a similar way and then add to the approach that I'm presenting here. So at the end, I would like to thank the guidance and support from my PhD advisor, Dr. Astrid Layton, and also from Dr. Richard Malik. And I'd like to acknowledge the support of Systems Engineering Research Center under two different contracts on parts of this project. So if some of you attended Dr. Malik's presentation yesterday, you might have seen some overlaps here. At this point, I'd like to thank you all for your time and attention. And if you have any questions, I'm happy to answer them now and also maybe in the chat later, or you can contact me using my email. Thank you. I'll stop screen sharing so that I can see if there are any questions in the chat.
Yes, Abheek, we have a couple questions.
See, yeah. So I see a first question. Have you investigated any relationship between your ecological network analysis degree of system order metric and interface complexity? I wonder if your results might inform systems integration effort and risk assessment. So yes, let me actually start sharing my screen again. I'm sorry. Sorry about the wait. So in the notional system of systems study that I presented, while it was a hypothetical operation scenario in which we had to do different tasks and we had different constraint systems for doing the tasks, they could be connected in many different manners. So the first design decision was, of course, to select the constraint systems that are going to be used. But then secondly, they could be connected, interfaced in different manners. And what I'd done was I'd grouped them into 4 different parts. So some of them would be more easier to work with each other than others, which accounted for the interoperability effects. So if you had too many interactions with systems that are not very interoperable amongst each other, then it did account for those effects in that it showed as a worse performance output because of the worse interoperability effects. I've not specifically gone into how interoperability effects and degree of system order are related, like finding a mathematical expression. But from the analysis that I did, I can definitely say that degree of system order does account for how many and how diverse interactions are being used in the network that is being studied. Does that answer your question, Dr. Wilson? And
Thumbs up, she said.
okay. Also, at the second question here is that at what point does system of system get too small to effectively distinguish one degree of system order from other? Yeah, I think that is a great question here. So this is again going into a little bit of heuristics, but we do have some evidence from the ecological literature that if we have networks with less than 12 or nodes, then at times the degree of system order differences would not be very meaningful. So, for example, if we look at a network that just has 3 nodes, it's very easy to go all the way from degree of system order of 0 to a degree of system order of 1, and that would not be very informative for us. So, yeah, I don't have a specific number here, but based on the literature, a cutoff at 12 was decided mostly heuristically.
Great. Thanks, Abhi.